Hello everyone and welcome to lesson 3 of the Pre-Calc / Trig summer course. As always, I'm Dan the tutor, your lovely host, and today we're going to be going over graphing functions and transformations. I'm going to tell you that this is a pretty important one. I mean, I think they're all important or else I wouldn't be talking about them, but this one is, I'm going to say, on the challenging side, especially compared to what we were doing before. But there's also going to be a lot of memorization after today because I'm going to ask you to memorize all, well, at least eight of the 9 graphs that are on this first page here. So without further ado, let's go ahead and start with the function f of x equals x. This is simply an equation that I'm just going to ask you for the general shape, by the way. I'm not going to ask you to graph the points like the xy coordinates. I'm just going to ask you to graph the general shape. So for instance, when we see the graph of f of x equals x, hopefully you know that this just looks like a linear line like that. In other words, it's in the form y equals mx plus b. This is known as a linear line. The name is linear. And it just looks like this. Obviously, you can have a negative slope, and I'm assuming you know how to do this already. The next function we're going to look at, it's the quadratic. Quadratic simply means it has an x squared in it, and that just looks like either a happy face or a frowny face if it opens downwards. So that's it for x squared. Again, you're very familiar with that. Now for one that you're probably less familiar with, it's the cubic. Cubic simply means x cubed. It's important that we know the general shape. It looks like this kind of curve that looks like this. Okay, it passes through the origin, although my graph wasn't the best. Who cares? It just looks like this with the 2 tails at the end. The next one is the square root function, one of our favorites. Remember that the square root function starts at 0, 0, the origin, and then goes up like this and continues in that direction. And there's no function on the left side. It just starts at 0, and that's because you cannot have negative square roots. The next one is called the cube root. What's interesting about a cube root is that we can have negative cube roots, which means that the graph will look like this. It's kind of a continuation of the square root as if it had another tail on the bottom side, basically. Next, we have the absolute value function. Not that bad. It's going to look like a V shape. And remember, absolute value simply means that whenever you have a negative number, you make it positive anyway. That's what you do. The next function might be one that you're not super familiar with. It is the exponential function. Does anyone here know why the number e is special or what it means? No? So basically, e is a number. It's called Euler's number. And e is a decimal just like pi that goes on forever. I'm just going to give you the first couple digits, 2.72. And the reason why it's special is because it's the most important number in calculus. Now, this is pre-calculus, so I'm not going to explain why e is special today, but it's the most common base you'll see. So it doesn't have to be e to the x, although this is the most common one. You can also have 2 to the x, or 5 to the x, or anything to the power of x. Now, the first thing you need to know about the exponential function is that it has a horizontal asymptote at 0. I know it's hard to see. Maybe I'll draw it in a different color so you can see it better. But it's a horizontal asymptote at 0. And then the graph is going to look like this. The left side is approaching the asymptote. The right side is approaching infinity, and it looks like this. The next one is a logarithm. And a logarithm is something that we'll probably be talking about in a separate lesson. But just today, we're talking about the shape. The shape is, it looks like a vertical asymptote, and it goes this way. In other words, it's kind of the opposite of the exponential function in just about every way. As a matter of fact, the two functions are inverses of each other, which is something we may talk about in another lesson. Now, again, one more thing worth mentioning. You can have, for instance, log x. And when you have log x, there is an invisible base 10 here, because every logarithm has a base. Like, for instance, you can have log base 2 of x, or what have you. But the most famous logarithm is the natural log of x, which is log base e. That's what ln is. It stands for natural log base e. And again, e is a special number, which I'm not going to tell you why today, but you will find out definitely next year in calculus. And then the last function here I'm going to cross out. I don't even know why I put it on here. That is a function technically. I learned it in my engineering classes, but there's no reason that we're going to talk about it today. So just cross that one out. I forgot to erase it. So any questions on the first 8 functions that we are going to be memorizing for the rest of the year? No?
Actually,
Oh,
I
go
have
ahead.
another question.
Yes, go
So
ahead.
I don't think you post the lesson 3 packet
I did not?
the email.
Okay, sorry. It is in the Google Drive, so you can definitely print it out after this. And
All right.
you can also listen to the recording. So, yeah, I'm sorry about that. I should have done that.
Okay,
But
that's okay.
yeah. Basically, if you're just following on a blank sheet of paper, that's going to work for today. Or if you just want to hold off and just wait for the recording, that's fine too. But definitely,
Okay.
whatever I'm writing down with the notes, just write them down so you have them.
hmm
Okay. Next, transformations. There's 3 kinds of transformations we're going to be talking about today. The first one is shifts. So what a shift is, basically, it's either up, down, left, or right. And the important thing to remember, if it's next to the x, then we're going to shift left or right. It's going to shift left or right. And I'll explain what that means in a minute. Then we can also shift up or down. That's basically if it's not next to the x. If it's not next to the x, then that's when it's going to shift up or down. Any questions with that? Okay, probably some of this sounds familiar to you from Algebra 2. Now, the first one's interesting because is that next to the x or is it not next to the x? Technically, for this first one, this can be both. In other words, you can either say shift 2 up because of the plus 2, or you can say shift 2 to the left. Now, why the left? Shouldn't it be the right because it's plus 2? Well, basically, a note we should add is that for the x direction, you need to flip the sign. And when I say left, the x direction, I mean left or right. So when I see plus 2, that really means to the left because you flip the sign. If I had x minus 2, then you shift it to the right because, again, you flip the sign. You do not do that for the y direction. This would just be plus 2, so up 2. That one makes sense. X is backwards. So here's why it works for both. If I take, first I'm going to draw the function x in like a dotted line, okay? This is the original function. It's supposed to pass through the origin. I missed, sorry. But x plus 2, that's simply a shift 2 units up, which is going to look like that, and then it go down that way. And in case you're wondering why 2 units left also works, it's because here's the spot for 2 units left, and then again it's a slope of 1. So the graph, I know I messed up again because it's hard to draw on this thing, but it's supposed to be identical to each other. That's the point. A shift up 2 is the same as shift 2 left, only for linear functions, only for linear, straight lines. Every other function in the world, it's going to make a difference, whether it's up, down, left, or right. So with that, let's look at the next example. The next example is the function e to the x minus 1. Now, I'm not expecting you to be a master of the shapes yet in terms of this is the exponential function. But what I am expecting is after next week, you are familiar with all the shapes of the functions and that you have them memorized, especially as you're doing the homework. So the first thing I'm going to do is I'm going to draw the original function as a dotted line, so we have a comparison. That is not an asymptote. I know this is going to get confusing because this function does have an asymptote, but it's just going to be shifted down 1. Shift 1 down. And why down? Why the y direction and not the x direction? Because the minus 1 here is not connected to the x. In other words, if I had e to the x minus 1, then you would shift 1 to the right, again, because it's the opposite than negative. And so that's when you have a shift to the right. But this is minus 1, not in the exponent, so it's a shift 1 down. So in other words, I put my horizontal asymptote there this time. I moved it 1 down. And for my actual function, it's basically the same exact shape, except it was shifted down 1. Now again, today, and for the homework, I'm just looking for general shapes. I'm not looking for coordinate points. This is perfectly fine. Okay, now for the next one. The next one, we have a square root function. We know what the square root looks like. And we also see that the plus 1 is connected to the x this time, which means this is going to be a shift in the x direction. And since it's plus 1, that means it's the opposite direction. In other words, shift 1 to the left. So once again, in the dotted line, here's my normal square root function. And I just want to shift 1 to the left, so it actually starts here, and then it's the same general shape, and it's going to look like that. And once again, what would it look like if it was a shift up or down? It would look like this. Now let me erase my circle because it looks like it's identical. So see the difference? This is an x direction shift because it's next to the x. This is a y direction shift because it's not touching the x. Any questions so far? Okay, and then just one more. You'll notice this last one has both a shift in the x and the y direction. So for the plus 2 here, x plus 2, that is going to be a shift 2 to the left. And the reason why it's left is because it's the opposite of plus 2. And then we're going to have a shift 1 unit down, and that's because of the minus 1 right here. So remember, it's an x squared function. Even though this looks confusing, many of you may be confused about what the graph looks like. But I'll tell you, first you're just going to do the normal parent function. We call the original function the parent function, and then the other one the transformation function. And then what I would say is you'd shift 2 to the left and 1 down, start at this point right here, and then it's the same kind of shape, this happy face. And that's how you do your transformations. Any questions so far? Okay. Next, we're going to talk about the next kind of transformation you can have. It's scaling. Scaling is basically, there's two kinds of scalings you can have. You can have a vertical stretch. A vertical stretch is when the number is greater than 1. So I'm going to call it c because c is a constant. For instance, in this example, c equals 3 because the constant's 3x. And whenever c is greater than 1, you've got a vertical stretch. That's going to make it stretch out in the vertical. In other words, it's going to kind of be smushed together and try and go up as fast as possible. Then you have a vertical shrink. And a vertical shrink is when c is less than 1. And that's going to make the function stretch out the other way. Another thing worth mentioning, there's another word for a vertical stretch. Vertical stretch is the same thing as a horizontal shrink. Depends on how you look at it. And then a vertical shrink is actually a horizontal stretch. So I don't care which one you say. I'm going to be focusing on the vertical names today because the vertical names you get from the actual function. If you want to know the horizontal shrink or the horizontal stretch, you have to take the reciprocal. In other words, the horizontal stretch or shrink would be c equals like 1/3, if you want to think of it like that. And that's very confusing, so I don't do that. So for this first one here, it's the function f of x equals 3x. So again, I'm going to draw my original function as a dotted line. And then the vertical stretch, since it's greater than 1, is going to make it stretch more vertically. It's going to look something like this. Now, obviously, this one has a slope of 3, so this one's easy to draw, but the rest of these are not going to be so obvious, so that's why I care about just the generic shape. So I'm going to write that down. This was a vertical stretch, and if you wanted to, you could also write a horizontal shrink. That would be correct as well. Sometimes you even say vertical stretch a factor of 3, and that's fine too. But I'm just going to accept vertical stretch for today and this summer course. Next, we have the 1/8. As you know, 1/8 is less than 1. That means it's going to be our vertical shrink, or you can call it a horizontal stretch if you want. And once again, I'm going to give as a dotted line the function, the parent function, which is x cubed. And then for the horizontal stretch or the vertical shrink, I'm going to make it look like this. See how it's kind of flattened like a pancake in the vertical direction? Or you could say stretched out in the horizontal direction? However you remember it, doesn't matter to me, but just know that the vertical shrink is going to make it look more flattened like a pancake. Now on to the next one. The next one is a challenge one because I put a combination of a vertical stretch and I also included a transformation in here. Now the number one thing that you're going to make a mistake of here, you're going to say shift 2 to the right. And this would be incorrect. This is not a shift of 2 to the right. And the reason why is because you cannot do the shift to the right if the x is touching like this. What do I mean? What I'm saying is you need to rewrite this function as the square root of factor out the 2. So you have 2 times the quantity x minus 1. There is your true shift. So we're going to say shift 1 to the right. And that's because you have to factor out the 2 first. You need to have it as x plus or minus some number. That's just the rule. We're also going to say that there is a vertical stretch here. And again, that's because 2 is greater than 1. The 2 being the stretch factor right there. So once again, I'm going to draw the parent function as a dotted line. Square root function starts at 0 and goes like that. And I need to do 2 things this time. Number 1, I need to shift 1 to the right, so right there. And then I'm going to have to make it longer than normal. In other words, it needs to look like this. See how that's bigger? That's exactly what I want. Vertical stretch. Any questions so far? And then for this last one, it's almost like the final boss of scaling and transformations, to be perfectly honest. Because this one, you'll notice there's actually 2 coefficients here. There's the 4 and the 2. So what do we do in that case? Let me tell you. The first thing we're going to focus on is the shift. In other words, I'm going to write 4 absolute value of 1/2 times the quantity x minus. If I pull out a 1/2 out of 1, that's actually going to make it a 2. Close parenthesis, close absolute value. And the reason why this makes sense is because if you distribute the 1/2 back to both terms, you're going to get the original problem, 1/2 x minus 1. Any questions on why I did that? When I pull out a 1/2, it becomes minus 2 instead. No? Okay, good. The next thing you need to do is you need to say what's the total stretch factor. That's going to be a combination of the 4 and the 1/2. Now, by the way, the 1/2 is technically already absolute value. It's already positive. So if you want to, you can pull the 1/2 out in front and just multiply, and then still inside your absolute value, you have x minus 2. That's perfectly fine. And because of that, this actually simplifies to 4 times 1/2, which is 2 absolute value of x minus 2. So in other words, we know what this is going to be. First of all, it's going to be a vertical stretch by a factor of 2. And you can also say it's going to be a shift to the right by 2. And so that's what that means. So it's a vertical stretch. You shift 2 to the right. First, let's draw in a dotted line what the function would look like. Remember, absolute value is that V shape. So first I'm going to shift 2 to the right there. And then I'm going to make it longer, which means it looks like that. It's going to look like a sharper V, just like that. Any questions on that one? Now, one thing I do want to mention, because this is where it can get kind of confusing, is that let's say I have the square root of 2x minus 2 again, because this is an easier example than the absolute value we just did. But what if I had this? What if I had absolute value of 2x minus 2 like this? Because remember, for this one we said factor out the 2, so you have square root of 2 times x minus 1, remember? But if I were to do the same thing here, notice that since the 2 is not touching the x, when I factor out the x, there's still the minus 2 outside the square root. In other words, because it's not touching the x, you don't factor out the 2. This is not going to become minus 1, which means in this example that I just made up real quick, this is again a vertical stretch, and we would also say shift down by 2 because of the minus 2. So I just wanted to make sure that was clear because this is really confusing, if you ask me, some of this stuff. I remember it took me many years before I really had this mastered. And even every once in a while when I do a lesson like this, I have to double think a lot of the time because a lot of it's confusing to me too. But the best way to get better is to practice, practice, practice. Any questions on anything from that page? Okay, we're on to the next page. The last of the 3 kinds of transformations we can have is the reflection. The reflection is basically you can have one of 2 kinds of reflections. The first kind is an x-axis reflection, and the second kind is a y-axis reflection. So actually, let me just show you what it looks like on a graph first before we look at any of these. So here's the x-axis reflection, and then I'll do the y-axis reflection. So as the name implies, an x-axis reflection, if I have a function that, let's just say, looks like, let me think. Let's say I have a function that looks like this. This is the x cubed function, if you remember. And this is the x-axis, this is the y-axis. If I flip this function along the x-axis, it's going to look like this in red. It's literally going to be the mirror opposite along the x-axis, okay? See how I did that? I flipped it along the x. Now for a y-axis reflection, let me do another function. Let's not do x cubed this time. Let's do a function like the square root of x, okay? So here's the square root of x, our favorite. Here's the x-axis, here's the y-axis. The y-axis reflection simply looks like this because I flipped it along the y-axis. And some of these are easier than others, that's for sure. But here's how you know what an x-axis and a y-axis reflection look like. For the x-axis reflection, it needs to go in front of the x. In other words, technically, this is like x cubed in parentheses because of order of operations. You do the exponent first, and then the negative sign's out in front. If you want to do a y-axis reflection, it's the opposite. In other words, it needs to be next to the x, so right there. And once again, it's confusing because the y-axis reflection needs to be next to the x, and the x-axis reflection cannot be touching the x. Isn't that great? Just so many things to remember. But are there any questions on this before we go into the examples? Okay then. So for the first one we have here, we have f of x equals negative x squared. So is this an x-axis or a y-axis reflection? Would someone like to take a guess? No takers? I will tell you. This is technically the parentheses around the x squared, so it's not touching the x. In other words, this is going to be an x-axis reflection. And remember, this one's the x-axis. So if my parent function is the squared, the quadratic, it's going to look like that, the parabola shape. And then the x-axis reflection, it's literally like you imagine you swish your paper hamburger style across the x-axis, and you're going to get a function that looks like this. That is our x-axis reflection. It's supposed to look symmetrical. So actually, let me try that one more time to make it more symmetrical. There, that's better. By the way, a fun fact for x squared, I would say that the y-axis reflection is going to look exactly the same. And that's fine. And again, the y-axis reflection would be this. Y equals negative x quantity squared. That's what a y-axis reflection would look like for this problem. But I don't have that, so I'm not going to confuse you. Okay, now for the next one. Again, we're turning up the heat because we have a shift and an x-axis reflection or a y-axis reflection in the same problem. So once again, whenever you have the 2 minus x, whenever you have this in the parentheses, the first thing you got to do is you want to make sure x is in the first position. In other words, what this really is negative x plus 2 cubed. And why do you want the x in the first position? Because that makes it easy for us to figure out what the shift is, left, right, up, or down. The next problem with this is I have a negative 1, or even just a negative sign out in front, which means I need to factor it out, and so it's going to look like this. Big open parenthesis, negative sign, a second open parenthesis, x minus 2, close parenthesis cubed. Now you may be wondering, how on earth did this make any sense? I'll tell you how. If you distribute the negative sign here, you get quantity negative x plus 2 cubed, and that's exactly what we have right there. So see, this is right. And again, why am I doing it this way? It's because now I can easily tell what the transformation is. So first, x minus 2, remember that's the shift, and that's going to be a shift 2 to the right because it's the opposite for left and right. And then the negative sign right here, well, since it's touching the x, and I know it's not directly touching the x because of the parentheses, but we're still going to say it's touching the x because you do it before the cubed. I repeat, you do it before the cubed because of those parentheses, outer parentheses. And because it's touching the x, we would say this is going to be a y-axis reflection. And so here's the y-axis. And so the first thing I'm going to do is I'm going to shift 2 to the right, Actually, first I'll show the parent function. It looks like this. This is, again, the cube function, okay? Now the next thing I'm going to do is always do the shift first. Let's make a note of that. Always do the shift first. That's a good rule of thumb for you. So we do the shift first. That means it's going to start here at that point right there. But then it's a y-axis reflection. Remember the y-axis reflection, it's going to flip it around left and right sides. So actually it goes like this on that side and down to the right on that side. And there's our function. Any questions there? Now some of you may be wondering, hey Dan, what if there's, you just said do the shift first, right? Well, what if there's a reflection and scaling? Which one do you do first, the reflect or the scaling? And honestly, it doesn't matter. Reflect/scaling, we would say the order does not matter. It only matters for the shift. So do the shift first, and then the order doesn't matter after that. So you don't have to worry. Any questions? Okay. Next, we have the absolute value of x plus 2. That's funny. I say always do reflections first. That's a typo. Sorry. That should say do the shift first. Sorry about that. Okay, next, we have the absolute value of x plus 2. You'll notice this is actually not a reflection at all. So I'm not sure why this is in the reflection category, but it doesn't matter. What is this? This is actually like the easiest example ever. It's literally just a shift 2 up. I have a feeling I definitely missed. Okay, there's supposed to be a negative sign in front of the absolute value of x plus 2. Sorry about the typo. It's supposed to be this. So erase that. So then the question becomes, what kind of reflection is this? Is it an x-axis reflection or a y-axis reflection? Well, the problem is you're not touching the x because the absolute value signs are in the way. So since it's not touching the x, it is actually an x-axis reflection. And so here's the x-axis right there. Again, this is what the parent function will look like. It's the v. And then you reflect it along the x. So imagine flipping it along that line. And you'll get, oh, I forgot to shift. Always do that first. That's important. So first you shift up 2, and then it goes the opposite direction like that. You actually get some cool kind of diamond shapes going on here. That's cool. And by the way, for the homework, you don't have to write the original function. If you want, you can just write the transformation. But I'm pretty sure in the answer key, I do have both the transformations that you need and everything else, just to show you how it shifts and how you compare it to the parent function. Any questions on that one? Okay, then good. And then the last one here, this one's cool. It's got a negative sign there and a negative sign there. In other words, this is both an x and y axis reflection. So how do we do that? Here's what I would recommend. First, again, we're going to graph the original function. This is what the natural log looks like, or any logarithm for that matter. It's got a vertical asymptote right there. So the first thing, it doesn't matter if you want to do x-axis or y-axis reflection first. That doesn't make a difference. Let's just say we flip along the x first. I'm going to draw this first transformation in red, and then I'll do the final one in black. So the first transformation looks like this. Okay, this is along the x-axis, just like that. And then if you want to flip along the y-axis, you got to move the red one to the other side, so it will look like this. Oh, I shouldn't do a dotted line. That's just confusing. The final answer is this black solid line that looks like this. The black solid line is our final answer. We did not move the vertical asymptote at all because there was no horizontal or vertical shifts. So this is our answer. Any questions? And by the way, there's no shame in drawing a separate graph if you really want to, because I know how cluttered this is. If you want to draw the functions in different steps, like let's say here's the parent function, right? And then in the next graph, you want to do the x-axis reflection, so you get that. And then in the final graph, you want to do the y-axis reflection, and you get that. That's perfectly okay too. You can do that as well. Of course, sometimes you have to draw your own graphs. As long as there's room to draw them, that's fine. Okay, and now for the next example problems, we're going to be doing something different. This time I'm going to tell you the parent function, I'm giving you the transformations, and you need to tell me what the function is going to look like. So I'm going to do the first function for us as an example. We have the parent function y equals x squared, and we want it shifted 3 units to the right and 4 units down. So in other words, remember 3 units to the right, that's the one that touches the x. So that means it's going to go in parentheses like this, and it's going to be 3 units to the right. Remember, right means minus because it's the opposite. So that's 3 units to the right. Then we're going to square it because that's what the parent function says. And then 4 units down doesn't go until the very end. And there we go. There's really not any other work you have to show for this. This is just like a one-step problem. You're either right or you're wrong. And I guess you'd get partial credit, for instance, if you had the -4, but you messed up the x minus 3. So there's definitely the opportunity for partial credit. But of course, I would recommend just get the right answer the first time, and then you don't have to worry about that. Next one, the parent function is the cube root of x, and we want it reflected along the y-axis in a vertical stretch by a factor of 2. So first, reflected along the y-axis. Remember, that means it's touching the x. Y-axis means touching the x. So when I do that, it's going to be y equals the cube root of negative x, because it has to be touching the x, and then it's a vertical stretch by a factor of 2. All that means is you're going to write a 2 out in front of everything. This is what a vertical stretch of 2 looks like. The 2 is in front of the cube root. Notice that. Always in front of the function part. And there's our answer. Any questions there? Okay. Number 3. The parent function is the y equals the absolute value of x. We would like a vertical shrink by a factor of 4, and we would like shift 7 units to the left. So it does, for this one, the order really doesn't matter as long as you get everything. The vertical shrink by a factor of 4, remember, vertical shrink is the fraction. That's going to be 1/4. So in other words, I'm going to say y equals 1/4 times the absolute value. And since it's a shift 7 units to the left, that does go next to the x, and it's going to be x plus 7, because plus 7 makes it a shift to the left. Any questions there? And this is the final answer, by the way. This is the final answer. Now, would it be right? Here's a question. Would this also be an acceptable answer? Yes or no? Any ideas? This is incorrect, and the reason why is because technically here, you'd have to factor out the 1/4. And when you factor out the 1/4, you actually get x plus 28. In other words, a shift 28 units to the left, which is not what you wanted. So better safe than sorry. Always put the 1/4 out at the front of the function, and then you don't have to worry about that at all. Okay, for number 4, the parent function is going to be y equals e to the x. We're going to reflect along the x-axis a horizontal stretch, which we'll talk about, by a factor of 3, and we're going to shift 1 unit right and 3 units up. So this is like everything. This has every trick in the book, basically. And that's okay, because we're going to nail it. So the first thing we'll do is reflect it along the x-axis. Remember, a reflection along the x-axis, that is not touching the x, so the negative sign is going to go out in front of everything. By the way, I'm just writing this function the first time. I am going to be changing it from out through this problem, which means I'm going to probably be erasing a bunch of times, so write lightly for these. Okay, next is the horizontal stretch by a factor of 3. Remember, a horizontal stretch is really a vertical shrink. It's a vertical shrink. And what that means is it's not a factor of 3, it's actually 1/3. In other words, I hate horizontal stretches, I hate horizontal shrinks. I want to get it back into vertical stretches and vertical shrinks because a vertical stretch is a normal number like 3, and a vertical shrink is a fraction like 1/3. So that means I'm going to put the 1/3. Let me just erase it here. I'm going to give myself some room. It's going to be negative 1/3. There we go. Now we've covered the reflection and I've covered the horizontal stretch. Now the only thing I need to do next is shift 1 unit to the right, That's not so bad. It's going to be next to the x because a shift to the right is touching the x, and it's going to be -1 because whenever you have to the right, you need to say minus. It's the opposite, as always. And then lastly, 3 units up, I just need to say +3 and make sure that's not touching the exponent. That is separate. And there we go. There's all 4 things in one fun problem. The good news is the next few problems are going to be like this one. And so we're going to just do a few more of these. And this is the last page. This is the last 2. Looks like we're going to finish a little early for this one, but I'm telling you right now, this is one of the hardest lessons in my opinion. And if you need to watch this lesson again at some point in the future, that is absolutely okay because this stuff is really hard. So for number 5, the parent function is y equals the square root of x. We have an x and a y-axis reflection. I actually like the x and the y-axis reflection because that means I get to think less. In other words, I already know it's y equals negative square root of negative x. Immediately, I know that. And the reason why is because it has to go in both positions. Okay, next, we just need a vertical shrink of 2. Remember, a vertical shrink really means it's a fraction, so that's 1/2. So in other words, the 1/2 does go in front of the square roots, so it's negative 1/2. And there's our final answer, just like that. Now here's a question for you guys. I thought you can't have a negative square root, but I'm clearly getting negative numbers right here. How is this possible? Any ideas? So basically the reason why is because whenever you have the negative sign here, it still needs to be positive numbers in the square root. So let me give you an example of a number that will work. X equals -4. When I plug in -4, you'll notice this is fine because it's a double negative. So this is actually the square root of +4, which we know is 2. So in other words, what this is saying is only the negative values of x will work for this function. And by the way, if you really wanted to, for any of the functions we just did, 1, 2, 3, 4, 5, and 6, if you want to, you can graph this because you know what the parent function should look like. So for instance, if I want to graph y equals -1/2 root negative x, I think that was it. Yeah. So what this function would look like, first, I would take care of the shift. There is none. Don't have to worry about that. If I want to draw the parent function looks like this for the square root function. Next, I can do the horizontal. Did they call it a horizontal? No, they called it a vertical shrink. That's fine. So vertical shrink was going to make it more flat like a pancake like that. But I really shouldn't write so hard with that because I need to erase it because it's going to be an x and a y-axis reflection. So this is the x-axis reflection, and then another y-axis reflection actually brings it over here. And don't forget that it's still smushed like a pancake. And this is what the graph will look like. Notice only the negative values for x are going to work here. And by the way, if you want to do the opposite order, if you want to do the y-axis reflection first, so in other words, this would be the y-axis reflection first, and then you want to do the x-axis reflection, you'll get the same exact answer. So you can practice with that if you'd like. And then all ready for the last question of the night. We have the parent function is y equals the natural log of x. We would like a horizontal shrink of 5, a y-axis reflection, and shift 2 units up. So the first thing I'm going to take care of is the horizontal shrink of 5. Remember, a horizontal shrink is really a vertical stretch. And what that means is you're going to keep the 5 the same. There's going to be a coefficient of 5 out in front. So y equals 5 ln x. That's the first part. Next, we want a y-axis reflection. Remember, a y-axis reflection is touching the x, because it's always backwards. And so that means it's actually natural log of -x, like that. And then the last thing you need to do is shift 2 units up. I love shifting 2 units up or down, because that just means you put a +2 or a -2, depending, at the very end of the problem. And there we go, that's it. Any questions on that one? Okay, and if there's no further questions, then that's going to do it for the day. So please do the homework. I'm going to, in a follow-up email, I'm going to send the recording, the lesson packet, because I forgot to do that, and the problem set, and then I'll post the homework in a few days. So thank you all for joining me today. I'll see you next week, and have a great rest of your night. Bye-bye, bye-bye, bye-bye.